And we will go back to our blackboard where we ended up, right? We were talking about complex. Hold on, I've got to share the screen and it's not working. Hold on. Hello. There we go. All right. Okay, so everybody can see the screen, I'm assuming. All right. So we stopped here where we're talking about, like, you know, the fact that the complex number is really just a pair of real numbers, right? 1, 2, or 1, 2, with an addition defined like this, and a complex conjugate operation, which is very different from anything we've seen so far, right? Which just takes all i's to minus I. Let me admit, Tyler again. Tyler, it just said you left and you're entered. I don't understand what happened. Okay. That was weird. Okay. Anyway, yeah, that was weird. It was like he was there, but then he was in the waiting room. I don't understand what happened just now. So I let him back in, but now he's gone. So I don't know what happened, guys. Something happened to Tyler. We're not sure what. Okay, so this operation complex conjugate takes all i's to minus I. That's a little weird, right? And I is defined, of course, like so, right? With this square root of minus 1, which of course means that I squared is
-1.
-1. What's I cubed?
Negative I.
Negative I, right. What's I to the 4th?
1.
1, yeah, etc. Yes? Like I to the 5th is what? One more, just for fun.
I.
Yeah, okay, etc. Right? Okay. So that's what these operations are, and that, you know, when you multiply a complex number by its complex conjugate, you get a real number. Okay. So for instance, for our two guys here, this z and this z, z and z star, we get x squared plus y squared, where this multiplication by these two numbers goes as a regular, you know, polynomial type multiplication, meaning, so if we say x plus iy, right? So this, sorry, let me, I want to start this with actual z star. Okay, so z times z star is x plus iy, x minus iy. Okay. And now we just do regular old multiplication with the rule that we know about I, that I is squared and minus 1. Okay, it's like a little bit of a construct, right, to make this multiplication of conjugates work in a funny way. Okay, so we do x times x is x squared, and then x times iy minus iy is minus ixy, then plus y times x is plus ixy, and these are, you know, these are just numbers so they can commute, and then plus I squared, sorry, not plus I squared.
Because it would be a negative.
Yeah, it's negative.
It would be originally be a negative
yeah,
y, and
negative
then when you
I squared y. Yeah.
It would be a plus.
I squared y squared. Right. So, and then we can see that these terms drop, and this becomes a this is negative 1, so positive. So x squared plus y squared. Now this kind of suggests, if we think about, you know, this idea over here where we have xy is this little point, right on this xy plane. This is that, you know, the y here are the imaginary parts of the number, imaginary z, and the x parts are the real parts, so real z. Okay, so in other words, that notation, imaginary z, is just y, not with the I, and real z, sometimes there's parentheses like this, is x. Okay, this kind of thing that you see, this z star z, giving this x squared plus y squared might suggest to you, that there's this another way of looking at a complex number, because of course we all know that there's polar coordinates that we can use like this, where this is r, right? And r is equal to z star z here in this case, which is equal to x squared plus y squared. Oh, sorry, r squared. Right? And theta is just equal to the arctangent, right? So theta is the arctangent of y over x, right? So of course that's just arctangent of the real, imaginary part of z over the real part of z. Those are the same thing, just different ways of writing it. Yeah. Okay. All right. So we know that, if you wanted to write the, a point x, y on the xy plane, because this is very similar to the xy plane, right? Okay. That you could write it in terms of, you could say, well, we know that it's z is x plus iy. I know that much. And I know that x is r cosine theta, right? So r cosine theta plus I r sine theta. And it turns out that this is r e to the I theta. You've probably seen this. You saw this in quantum mechanics before. But why is that the case? Well, if we look at e to the I theta, right, we know that you can expand that in a series. So we can go from n equals 0 to infinity. That's what this is equal to. And then we have I theta to the n over n factorial. That is the expansion of that, right? That's the series expansion of E, right? So like e to the x is sum over n equals 0 to infinity x to the n over n factorial. But here I don't have x, I have I theta, right? So it has to go here. And you can probably tell that if we started doing the sum, right, we would have different signs on this because of the I squared and the I cubes and the I to the fourth and the I to the fifth, etc. Right? You have different things. Sometimes you'd have positive or negative 1, right? When you have odd powers, even powers, right, of I, you would have like positive, negative 1, right? So for instance, here we had I to the 5, let's just do I to the 6th, right? I to the 6th is what?
-1.
-1, see? So if you have the even powers, you get just 1s and -1s, right? But for the odd powers here, you get i's, plus or minus i's, right? So you get back a complex number like we have here. And if you actually do a bit of work, and it is a bit of work, you can write down that you can split this into those two types, right? The type that has it has just the ones, and the type that have the i's. So you split them, right? And so we have something that looks like this. I'm going to use a different index here. And we'd have, just looking over at my notes, that's why I'm looking over here. -1 to the nu, and then theta to the 2 nu. So these are the positive, these are the even powers, right? And 2 nu factorial, then plus I times the sum of nu equals 0 to infinity, -1 to the nu again. But now we have the odd powers of theta, 2 nu plus 1, okay, over 2 nu plus 1 factorial, right? So we've split this into the even and the odd powers, right? These are the even powers in this series. These are the odd powers in this series, okay? And there's an I in front of the odd powers, as we know. You're always going to have an I. It's either going to be plus or minus, depending on the power, but it's going to be, there's going to be an I in there, right? Well, it turns out that if you go look up the series expansion for cosine, this is it. And if you go look up the series expansion for sine, this is it. And I hope it makes sense to you that the even powers are the cosine, because cosine's an even function, and the odd powers are the sine, because sine is an odd function. So that's where this whole thing comes from, okay, is this little proof. Not really a proof, because I didn't really prove it, but hope you believe me. Okay, so this is another way of writing our z. All right, and you've seen this before in quantum mechanics. Okay, now let's think about what is, just give an example. So what is e to the I pi over 2? What is that? Can you guys figure that out? Put it in the chat if you know it. By the way, if you guys are confused about what to do, use this formula right here. Where's my, there we go. It's very cold here today. Not quite, Jackson. Oh boy, 61 degrees. Yes, Jackson, good. Anyone else have an answer? Chat it to me privately in the chat. Seems like Tyler's having some internet trouble today. Sorry about that, Tyler. That sucks.
What was that?
No, it just sucks that you're coming in and out there.
I don't know what's happening. Like I go and I try to press a button and my screen just gets frozen and then it says Zoom isn't responding.
That's
Please
weird.
close the thing or whatever. So I had to get on my phone the first time because
Yeah.
there's something wrong with
Maybe
my laptop.
Sweetbriar's having trouble with their internet.
Maybe. I don't know.
Honestly, it sounds like, because I had that problem sometimes, it sounds like it could be that your disk is full. Open Task Manager to see if it's.
I know it's not full because I've had this problem going on well, it happened like a month ago. Something's going on. And I checked it and it wasn't that.
Right.
And what did I do last time? I think I just unplugged the battery and plugged it back up and let it reboot, and it just kind of like turned it off and back on again. You know, that type of deal. I don't know. We'll see.
All right, anyone else have an answer? No. Okay, what is R, Tyler?
Oh, yeah, you're right. Oopsies.
It's okay. Yeah. All right, should we go over it? Everybody? Okay, so let's use this formula here, right? So we have R e to the I theta is this stuff. Okay, so what is theta in this equation over here?
2 pi, and I guess in radians.
Pi over 2.
Pi over 2, sorry.
Yep, right. Good. What is R?
It's just 1.
Just 1. Yeah. Okay, so let's use this here. So we're going to say this is going to be equal to 1 times the cosine of pi over 2 plus I times the sine of pi over 2. What's the cosine of pi over 2? 0. What's the sine of pi over 2? 1. That's right. So it's just I. Okay, one more time now that you saw. What's e to the I pi? Good, Tyler. Good, Zoe. What does that say? Oh, it says,
It capitalized it. It's supposed to be I.
oh, yeah, no.
But really?
Yeah.
But I thought cosine was negative. Of pi was -1.
It is.
Oh wait.
There you go, Jackson. Good. Anyone else? Yep, Andrew. Good. Okay, should I give you there we go. Haley, good. Jeff, good. Awesome. All right, guys. Excellent. Yes. So obviously, this is the same idea. So cosine of pi plus I sine of pi. And of course, sine of pi is 0. And the cosine of pi is -1. And so we just get -1, right? Okay. All right, so let's think about where would we draw this first one? What does e to the I pi look like on my imaginary plane drawing? Sorry. Where's the first one? E to the I pi over 2 look like? What does that look like? Where should I draw a dot? Where is it on this plane?
You go up 1 unit.
Yeah.
If that's the XY plane.
Yep. It's right here at I. And where do I draw e to the I pi?
Go left 1 unit.
Yeah. Right here, -1. Yeah? Okay. All right. Great. So e to the I pi is actually real, even though it doesn't look like it's real. It is, right? Isn't it? Yeah. Okay. All right. One more thing I want to cover, and then we can adjourn for the week. Can I get another layer now, guys? Yeah.
Yep.
Okay. So one is, how do you find the real and imaginary parts of things? Well, you know, for instance, if you have z equals x plus iy, then the real part is this, right? So real of z is equal to x, and imaginary z is equal to y, right? So that's really easy. That's nice. Okay. And because sometimes you need these parts, you need to take it apart. All right. But if it's not in this form, it might be a little harder. So let's look at z is equal to e to the I theta. Well, you don't immediately know, oh, so r e to the I theta, sorry. You don't immediately know what that is. But if you write it out a little bit, as we know, we just were looking at, I can identify what the real and imaginary parts were, right? So the real is here, so this is real z. And the imaginary part is here. This is imaginary z, right? Okay, so if you notice here, if I wanted to take the complex conjugate of z in its sort of standard form x plus iy, I would just make the I go to minus I. And for the z in the polar form, it's the same deal because I can write r e to the minus I. Oops, sorry. That was that was dumb. Give me a second. I just messed this up big time. Okay. So z star in the polar form is just going to be e to the r e to the minus I theta, because if you think about it, let's, you know, right, if you think of it as negative theta here, right? So if we think of it as negative theta, so let's just delve in a little bit here. So we go r, right? And then we go cosine of negative theta plus I sine of negative theta. Then the cosine's even, so it doesn't care about that. So this just becomes r cosine theta. The sine is odd, and so it pulls out a minus sign. So minus I sine theta. And that's why this is the complex conjugate, right? Okay. Okay. Now, if you're not in one of these standard forms, it's really hard to tell what the real part is, what the imaginary part, what the complex conjugate should be. For instance, if you have something that looks like this, 1 over, you know, a plus ib. Okay. Is the complex conjugate just sticking in minus I in there? No. You have to actually make it into one of these forms. Take your pick. It's easier to put in one than it is to put in the other. But you got to put it into one of these forms first before you can write down what the complex conjugate is. Yeah, Jackson.
Okay, for the last one, would the imaginary part be negative sine theta?
Yeah, here. Right. So
Good.
here, yeah. So no, so for here, the imaginary part is r sine theta. Oh, and I forgot the r. I'm so sorry. And so if you wanted the imaginary part of the complex conjugate, it definitely is going to be negative r sine theta. Absolutely, right? Because the complex conjugate has that opposite sign on the imaginary part. Yeah? Yes? Okay. All right, so what are we going to do with this? How are we going to fix this so that we get it into, say, this form? Anybody know how to do that?
Multiply the top and bottom by a minus ib.
Yeah, so you're going to multiply the top and bottom by the complex conjugate of this bottom part. Okay, so we're going to say we're going to multiply the top a minus ib and the bottom by a minus ib. And so that's going to give us on the top just a minus ib. And on the bottom, it's going to give me a squared plus b squared, right? So now tell me, what is the real part? What is real z?
A over A squared plus B squared.
Uh-huh. And what is imaginary? Z.
B over A squared plus B squared.
Um,
Negative B squared over
there
A
you go.
squared.
Letter
squared.
B over A squared plus B squared. What is Z star?
B B squared. A
Hmm?
B over A squared plus B squared.
Mhm.
I don't know.
What do you do to take the complex conjugate? Once you have it in this form, because you have it in this form now, right? Because if we look down here, I'll just write it one more time. We have A over A squared plus B squared, right? Minus I B over A squared plus B squared. This is like X and this is
So
Y, right?
wouldn't the negative cancel out and it'd just be regular B squared over A squared plus B squared?
Now I'm not multiplying by a complex conjugate. I'm just asking what is the complex conjugate?
Oh, that would just be A plus IB
Right.
over.
Over A squared plus B squared. Yeah. Okay. Okay, so what about let's see. Let's see if we can do this last example. All right. Let's look at the real and imaginary parts of this. -1 plus I times the square root of 3 all over 2. So this is Z cubed. Now, I'm not going to make you guys do this. I'm going to show you a little bit what to do. So we would, if we had this, cubing this is going to be a pain in the butt and easy to make mistakes. But if we could write it, if we could write this whole thing inside, right? So I'm going to call this, I don't know, I'll call this Z prime or something, right? So if we could write Z prime as equal to, R e to the I theta, so in that form, then cubing it would be super easy, right? Because Z prime cubed is just going to be R cubed e to the 3I theta, right? Super easy. Okay. So how are we going to figure out what R is and what theta is for my Z prime here? How do I figure out what R is? No. What do you think?
This is the -1/2.
I'm sorry, what?
This is the -1/2.
It's -1/2. Okay, how'd you get that?
I just kind of got through it. I don't know.
Okay, right. Okay. Well, let's see. So we know that R squared, right, is Z star Z, isn't it? Or Z prime. So let's write that down. So we know that R squared is Z prime star Z prime, right? We know that's true. Okay. Because remember, for our usual thing, we have, R squared is X squared plus Y squared, which is Z star Z. So I'm just taking my inner one here. I just need to find out what this inner Z prime is, right? Okay. Okay. So what is Z prime star?
-1 minus I to square root of 3 over 2.
Yeah, all over 2. Good. And then my Z prime is just -1 plus I square root of 3 over 2, right? Okay. Well, so we can write this out, or we can just look, right? We can just look and see what it's going to be. So it's -1, -1/2 squared, right? Plus square root of 3 over 2 squared. Yeah, that's the x squared plus y squared. This is the x This is the y. Yeah, or we could, or feel free to by hand and prove this to yourself, but right, okay. Okay, so that's 1/4 plus 3/4, which is just 1. Yeah, did I do that right, guys? So that's what r is. So what about theta? Remember, theta is this arctangent of y over x, right? So we have y, which is square root of 3 over 2 over x, which is minus 1 over 2. The 2's are going to cancel out there, and I'm going to get just the arctangent of the square root of 3 minus the square root of 3. Yeah. And it turns out, I'm not going to bore you with the details, but it turns out that that is minus pi over 3. But you could easily figure that out. Okay. Yeah. So far, so good. Okay. So now I know what my z prime is. Yeah. So z prime is equal to 1. So r is 1. E to the I to the minus I pi over 3. And z prime cubed, which is what we're after, is r cubed, which is 1. E to the 3 minus 3 times I times pi over 3, which of course is just e to the minus I pi, right? And that is just 1, right? So that means that this whole thing is really not a complex number at all. It's a real number. So the real part is 1, and the imaginary part is 0, and the complex conjugate of z is just z, right? Because there's no imaginary part. I know I went through that pretty fast. Any questions on that?
I guess the only thing is that it doesn't look like it would cancel out, because like if it was squared, then it like the eyes would just cancel when you multiply it. So I mean,
Well, squared, no, squared, the eyes would not cancel. Yeah,
that's
you have
just
to have the complex conjugate for the eyes to cancel out. When it's
Okay.
not the complex conjugate, it definitely doesn't cancel out.
all right.
Yeah. So, yeah, interesting though, right? You wouldn't think that's 1, but it is.
Hmm.
Yeah. Okay. I think we're gonna quit there. We're gonna quit 10 minutes early, and we will start up our neural network stuff on Monday.
Okay. Thank you.
Okay, guys. See you later.
Dr. Shane,
Bye.
Bye.
Yeah.
for this weekend when I meet with Jude, is there anything else we should go over besides this, or?
Well, I mean, we've done some stuff before this, right? All the
Yeah, we've actually been keeping up, which is cool. So,
yeah, good. Yeah.
But yeah, I was just gonna double
I
check.
can do more examples like this with you.
Okay,
Okay.
thank you.
Sure. All right. Bye.
Yeah.